Good morning to everybody. Our Honorable Vice Chancellor already joined, Professor Soikat Moitra. Good morning, sir. And
Dr. Giri, kindly start the meeting.
Hello. Our Vice Chancellor has joined, Professor Soikat Moitra. So, sir, start. So, sir, Professor Sakurai, Japan, and Professor Meng, he's from Denmark, and Anjita Pal, he's from Madras.
Okay.
And you see today.
Dr. Giri, you have disconnected, got disconnected. Kindly reconnect.
Giri sir, please unmute your mic, sir. Giri sir.
You kindly unmute. Your voice is not clear. I think there are certain problems, technical issues at Dr. Giri's side. Dr. Moon, let us start.
Please, sir, please carry on.
Yeah.
Okay, so can I, so can I start, right?
Yeah. Just I'm just introducing you to all our participants, and then you will start. Dr. Giri, who is our coordinator, probably some technical reasons, he is not in a position to come. Dr. Giri, can you continue?
I say yes, sir. Are you getting my voice?
Yeah, now it is audible.
Are you getting my voice, sir?
Yeah. Continue.
Okay. So welcome to everybody, and I am Dr. Devashish Giri, Associate Professor at the Department of Information Technology of Maulana Abdul Kalam Azad University of Technology. Today is the session 4 of the webinar series of cryptography, network security, and cyber security.
Right.
And it is jointly organized with MAKAUT and Islamic University of Science and Technology. Now we are in our inauguration ceremony. We are having our Vice Chancellor, Professor Soikat Moitra, and Professor A.H. Moon. He is from Dean of Islamic University of Science and Technology, and our three eminent speakers, Professor Sakurai from Japan, and Professor Dr. Meng from Denmark, and Dr. Anjita Pal from IIT Madras. So now I request our Honorable Vice Chancellor to say few words to the audience.
Thank you, Dr. Giri. It's a proud privilege for me to initiate this today's webinar, which is 4th in a row. And this topic is very interesting and important because in this context, cyber security, data security, network security, cryptography, all these areas are getting paramount, this importance, because many things, almost everything is happening in digital domain. And that's why the security of these digital platforms, particularly this data from individual perspective, from organization perspective, that is a crucial importance right now. And the nice thing is, because this is one of the blessing of this pandemic scenario, that we are in a position, we are being able to invite doyens and experts in these fields from different parts of the world. And today also I am seeing a galaxy of experts. Dr. Y. Meng from Denmark. I can see the picturesque the city of Denmark just behind him. Then Professor Sakurai Koichi from Japan. Thank you for responding to our call and agreeing to share your experience and wisdom for the benefit of our participants. And we have also Dr. Orinjita Paul from IIT Madras. It's nice to see all of you. And as this is a collaborative venture with Islamic University of Science and Technology and Maulana Abul Kalam Azad University of Technology that belongs to us, Professor Moon is from there, Islamic University of Science and Technology, long time associated with us, and he is himself is an persons with solid technical knowledge, and I believe that today all our participants, they will be immensely benefited from this knowledge, from the experiences, from the presentation deliberations, as shared by all these participants, all these panelists. And with this, I would like to congratulate Dr. Giri for inviting, for arranging this so many experts in this field, and organizing the fourth time in a row this program, particularly this network and cybersecurity. And after this, what I think that if you can initiate publishing a compendium of all the lectures and deliberation presented at this webinar in these last three occasions and today's webinars also, then it will be a great asset for our learning community. So with this, I'd like to conclude, and I'd like to request Dr. Giri to take this session away and to invite our experts to give their presentation and share their knowledges. Thank you.
Thank you very much for your speech to the audience. And now, sir, I request to Professor Moon to say a few words to the audience.
Thank you very much, Professor Giri, Honorable Vice Chancellor MAKAUT, Professor Maitro, and good morning and Assalamu alaikum from Islamic University of Science and Technology to all the learned speakers and participants. It has been absolute privilege and pleasure from the Islamic University and Science and Technology side to be associated with such great initiatives of MAKAUT in organizing these qualitative webinar, a series of qualitative webinars. I personally have interest in this particular domain. Therefore, I thoroughly enjoyed the last session in which learned speakers talked about different techniques, techniques of generating digital signatures which are computationally efficient. Particularly the talk which was on proxy re-encryption schemes and its importance in the context scenario. Professor Maitro rightly said that any crisis actually breeds innovation. So I believe we are all in the process of innovating ourselves, learning new technologies, learning new things. So I'm looking forward to this session. Particularly, in the context of the new networks which are emerging, wherein it is no longer host-to-host communication, but the focus is on content-centric networks. So in content-centric networks, wherein we are using resource-constrained devices, there are huge security challenges. You cannot simply apply the run-of-the-mill or conventional cryptographic protocols to secure communication or messages which is occurring in the content-centric networks, for example, IoT, which actually thrives on using resource-constrained devices. So I'm looking forward to the research, directions, research directives from the learned speakers in this particular area, so that they would particularly identify the kind of web resources which are available, the kind of validation tools which are available when they actually try out different experimentation. So over to Dr. Debashish, and thank you very much, Honorable Vice Chancellor, for providing such a dynamic leadership, both at the MAKAUT as well as I equally thank the Honorable Vice Chancellor of Islamic University of Science and Technology, and you too enjoy a great Bohemia. Thank you very much, sir.
Dr. Giri, Dr. Giri, kindly start the session. Kindly start the session, Dr. Giri. I think
Yes,
Dr.
yes, sir.
Main will make his presentation fast.
Yeah. So our first speaker is Dr. Uji Meng, Technical University of Denmark. I request to Dr. Meng to share your slide and start the presentation.
Okay, so can I share my slides right now?
Yeah.
Okay, thanks. Okay, so can you see the slide?
Yeah, we can see.
Okay, yeah, thank you very much. So first, I'd like to thanks for the invitation, right, to attend this webinar. And I think it's really good. So today my topic is about actually, so how to build the touch behavior, the user authentication schemes on the mobile devices, especially the smartphones. So I'm Weiji. So now is working at the Department of Applied Mathematics and Computer Science at the DTU, so in Denmark. So DTU actually, so it was founded in 1829, okay? And right now it's a member of the Eurotech University Alliance. And these are just some pictures. So it's the same like my background image, right? So yeah. So these are some pictures from DTU. So actually you can see the left, the left, there are some the buildings, and inside the buildings, there are some of the classrooms there. And these are also some more pictures, especially taken in the summer. So in the summer, so I think because due to the COVID-19, right? So it's very hard right now for us to meet in person. So, but actually, there are many students actually they will like sit together during the lunchtime or the spare time, right, in the campus. So actually during my talk, if you have any I think if you have any questions, you can leave a message in the chat. So maybe later I can check all the questions and it's easier. All right, because due to the collection, maybe it's not that clear if you speak out the question. And then let me introduce my research areas. So my basic research is on the intrusion detection, right? And if you have some knowledge, or if you are familiar with intrusion detection systems, right, the IDS, then you know it has been developed for over 40 years. So as a technique, right, it's relatively mature. So right now the trend is that to apply the idea of the intrusion detection to other areas like the biometric authentication. It means that to authenticate whether the current user is legitimate or not. So today's talk is just focusing on this area, and also the trust computation, or we call the trust management. So it aims to identify some insider malicious nodes within a distributed system or network, because we know, so right now most systems or networks, they are distributed, right? So and even for the intrusion detection systems, right? So right now we have the distributed intrusion detection system or collaborative intrusion detection network. So the insider attacks are the main challenge, right, to such kind of the network. And later is the HCI security. It means the human computer interaction security. So the main purpose is to evaluate the usability, right, of a security mechanism or security application, right? So for example, the graphical password. Graphical password means that we do the authentication based on the interaction on images rather than the streams or traditional the text, right? So there are many there could be many interesting topics there. And I think maybe you are not that familiar with the graphical password. So one practical application is the unlock mechanism on the Android phones, right? So there are 3+3 dots, so you can input an unlock pattern to unlock your phone. And the last one is the smartphone security, right? So some of my research are focusing on the side channel attacks, like the phone charging attacks. So there could be many the topics here, right? And of course, there could be other technologies like the blockchain, right? And some other techniques there. Okay, so this is the outline of today's lecture. So first, I will introduce the background of the biometric authentication, and then I will introduce two earlier studies on this topic. Where actually the first two studies on this topic, because after that, normally the development is very stable, actually, based on to provide some improvement over these early works. And last, I will provide some insights and discuss some open challenges, right, regarding this topic. Yeah, because I cannot see the chat right now, so maybe I can chat. I can check the questions later, if you feel okay. So first, let me introduce the background. So for the user authentication on mobile devices or in our PC, right? So normally there are three basic methodologies that we can have. So first is based on what you know, right? It's easier, right? For example, your ID, your password, right? Or the PIN code. So everything in your brain, right? So you know that. And the second is what do you have, like the cards, the keys, the badges, right? Anything you have on your hand, right? So you can use the objects, right, to show and authenticate yourself. And the third one is what you are. It means that based on the features of our physical body or the behavior, right, like the fingerprint, the face, iris, the retina, right, that we have. So yeah, and of course, so right now the first method, right, the password actually is the most widely used user authentication method right now. But we know there are many limitations and challenges when we use the password, right? There could be some external threats like the malicious applications, the malware, right? Because the attackers, they can try to induce the users to install, right, some malware so that they can store your passwords. And also in a crowded place, because the attackers can see your password, right, where the should serving or some other easy attacks, or some the recording attacks to record your phone screen. So it's easy to obtain your password. Another issue is the internal from internal, for example, because the users, because we suffer from the long-term memory limitation, so we cannot remember random complicated string or text for a long time. So in that case, the users may choose a simple, right, a simple password instead. So it may greatly degrade the security. And then, so right now, the research actually moved to developing the biometric authentication, or combining the biometric authentication with the traditional, authentication, the password authentication, right? So for the biometric, it means that the method of authenticating users, right, like their measurement and the enduring the human physiological or behavior, the features to model and represent a user's identity. So we can see there are the basic approaches. One is the physiological, right? So we can use the measurements from the human bodies, such as the fingerprint, the face, retina. And another one is the behavior approaches. So we can use the measurements from the human actions, such as the voice, and also the signature and the keynote, right? How we use the keyboard and also the mouse, right? And also the touch dynamics, because right now we have many the touch screen enabled devices, right? So it's very popular right now. And there are some the basic behavioral biometrics. So first is, as I mentioned, the voice, right? Voice actually, I think you are familiar with it, right? Because there are also some the applications on smartphones that you can try. So you can try, and also if you use the Siri, right? There, yeah, you try it. And the second one is the signature. The signature, I think you are also familiar with it, because right now, if you go to the bank or if you do some transactions online, so later you have to sign your signature actually online. So it's a virtual signature. So you can use a pen or you use some other some means to improve the signature. And the second one is the gate, and the gate recognition. I think it's interesting. Actually, we use it to model a user when you work, right? So we can build a 3D model, right, of the user and try to authenticate how the user works. But we know that there could be some challenges there, right? Because when you get hurt or if you are not feel good, so maybe you work in a different way, that may increase the error rates during the authentication. But it's still a very interesting area or the direction, right, on the biometric authentication, on the behavior authentication. And then the behavior profiling, which means that we can model how the user, right, use the mobile devices. For example, in the morning, how many or which applications the user may use and in what sequence or order, right, he uses it. And then the keystroke dynamic, that how you use your keyboard, right? How you, there are many studies on the keystroke dynamics. Okay, and right now, with the popularity of the touch screen, so the research has moved to the touch dynamics, right? So it means that to authenticate the users based on their touch behaviors. And for the behavior authentication, so we need to think about, right, whether we need the behavior authentication, because I will discuss later, because the error rates, right, may be higher, right, than the traditional authentication. So first, we need to think about the security requirements and the behavior authentication. Usually, we support we can use it in an environment which requires a high security level, right? So because we can bear the cost there. The second one is the performance and security accuracy, right? So whether you can bear some error rates there. And also we have to make a good balance between the usability and the stability, right? So actually all are regarding how to make a balance among the security, usability, and the stability, right? Okay, then let me introduce some of the state-of-the-art. So actually, when we can perform the touch behavior authentication, the first is that we have to be able to identify the touch behaviors, right? So luckily, so in 2009, there are many studies they are working on how to identify the touch behavior. For example, in 2010, right, they developed some the hardware so we can identify the multi-touch behaviors and multi-touch interactions, and this is the basis for the touch behavior authentication, right? Because the hardware, we need the hardware, the support from the hardware, and then it's from Florida. So they show how we can identify, right, some more concrete the multi-touch behavior, like the zoom in or zoom out, right, or some other the multi-touch events there. Okay, so then let me introduce two early studies on this topic. So first talk is actually published in 2012. So in this work, actually developed a user authentication scheme based on touch dynamics, including 21 the touch gesture based features. So and they analyzed the differences and the similarities, right, between the touch keynote and the keystroke and also the mouse dynamics. There are some differences because the touch dynamics is different from the keystroke dynamics, right? Because the touch dynamics has more input types, such as the multi-touch and the touch movement, right? So because we can perform on our mobile devices. And the keystroke dynamics only has the buttons, right? In old days, only has the buttons, so we can use it as the input means, right, to interact with the devices. And then there are also some similarities. For example, the press button up and the press button down is very similar to the actions of touch press up and the touch press down, right? And also for the mouse dynamics also have the movement there. So it's similar to the touch movement there, right? So why we analyze this? Because in this case, right, we can adopt or to exploit some similar features from the keynote or the mouse dynamics, right, to actually to model the touch behaviors. So we can borrow some features, right, from other. So then we classify three actually the input events, right? So first is the single touch. So we only use one finger, right, to input to interact with the touch screen. The second is the touch movement, right? So we perform a movement there, finger movement. Then is the multi-touch, right? We used two fingers, right, at a time, right? So to interact with the screen, So it's, I think it's easy to understand. So I will continue. So this is the basic architecture, right, for building the touch dynamics-based authentication system or the touch behavior authentication system. So basically, the architecture is almost the same across different works. So there are the key components: the data collection, behavior modeling, and the behavior comparison. The data collection, right? We have to collect the raw data from the touch screen, like the coordinates, right, and also the touch, the speed or the touch direction, right? And then so we have to apply some techniques to model users' behavior, right, and extract the features from the collected raw data. The last component is the behavior comparison. So we have to compare the current user's behavior with the pre-built, right, the user model to decide whether the current user is legitimate, right? So actually here we can apply either machine learning techniques or some statistics approaches here, right? So to help us to model and compare users' behavior features. Okay, at that time, actually, I think in old days, right, in around 2012, right, so it's not that easy to collect the raw data and you get the data from the mobile devices. So at that time, so you have to know the basic, right, architecture of the Android OS, and then, right, we can modify some layers like the application layer. So we can insert some of the OS recording commands, right, to help us to record the data. So at that time, actually, we use Google Nexus 1, the Android phone, right? So with a touch screen. And if you read some papers, right? So in 10 years ago, right? So normally we will use this Google Nexus 1 mobile devices because it's provided by Google for the researchers, right, to do the research on the mobile security, right? So yeah, the advantage is that because we can store the Android OS and we can replace it with a modified customer version, right? So it's good. So at that time we use the, actually we update the phone and with a modified Android OS version. So based on the side-channel mode, right? The modification mainly changes to the application framework layer to help us record raw input data from the touch screen, such as the touch input, the types, and also the coordinates there. And then we install a separate application, right? So allow us to extract the record data from the phone. And this figure shows the raw data, right, which we obtain from the mobile devices. So we can see the input type, the X and Y coordinate, and also the time. We have to see the time is the system time, which is the depends on the start of your mobile devices. But we don't need to understand it because we only need to know the difference between the time, the system time, so we can calculate the features, right? Like the speed and also the angle there. And here, because at that time, for example, we use the machine learning techniques. So in that we have to train the classifier. So in that case, we have to determine the session. So how many the touch events, right, should be included in a session starts in a session, or how long the session could be, right? At that time, right, we just use a time-based session, right? So we set the session to be 10 minutes, right? And also because there are many discussions can be made on the time-based session, because you can choose 10 minutes or but you can also choose 20 minutes or half an hour. So it's up to the scenario, right? And also your user stories. So here, but at the time we only choose the 10 minutes. And this is a feature that we defined. So we have 21 features to have a model user, right? So the features are including the average touch movement speed per direction. So because we divide a 2D, right, into 8 directions, I will introduce later. The second is the fraction of touch movement in each direction. So we have another 8 features. And then we have the average single touch time, average the multi-touch time, the number of touch movement, the single touch event, and the multi-touch event per session. So in that, we have a total of 21 features there. So as I just said, so the figure shows that we have 8 different directions because we divided the 2D, right, into 8 directions. And in that end, we can use the touch movement speed and touch movement angle. So we can know the average touch movement speed in each direction, right? So we did know that the ATM, right? The feature, yeah. And then is that the figure shows the average touch movement speed, right, versus the direction of the movement for different users. So we can see actually different user, the features, right, are different. So in this case, we can use the feature to distinguish 2 users. So it's feasible. And this figure shows the fraction of the touch movement versus the direction of movement for 2 different users, right? The fraction, right? So also we can see, right, the features are different among the users. So it's also feasible for us to use this feature, right, to model different users. And then the average, the single touch and multi-touch, the time, because somebody may perform a touch very quickly, right? So maybe the time, right, are very small, but maybe some other users may press very heavily and maybe the time is very long. So we can see the 2 users actually they perform differently when they use a single touch or multi-touch. And then is the number of the touch actions events, right? Because somebody may prefer to use more the touch movement events, or some of you may prefer using multi-touch more, or just a single touch. Right? It's up to the habits of the users. So we can also use this feature to model the users. And then we use the machine learning algorithm. So that means we have the classical, right, the training and the comparison phases, right? For the training, of course, we have to use the data, the label data, and to train the classifiers. And in the comparison phase, we have to compare two profile and make a decision. And then evaluation. At that time, we actually we adopt the 5 classifiers and actually extracted from the open source platform, right? This decision tree, the Z48, and also the naive Bayes, and also a baseline classifier, K-star, and the 2 neural network, the RBFN and the BP. Right. So because to avoid any implementation bias there, so actually we extract the classifier from the WCAR platform, and I can see right now many researchers they extract the algorithms or the classifiers from this platform because it's an open source, right? The machine learning software, the collection, so it provides many machine learning algorithms there, so it's easy to use. Okay, and for the user study, so we recruited 20 Android phone users because it's 10 years ago, right? But right now, normally you need at least 50 users in your study to validate the results. And there's just some the background on the users, right? So before starting the collection, we have to describe our objectives and our purpose to all the participants. And then we need to get approval, right, from your department or the university, and also from the participants to agree, to make an agreement there, especially for the data collection. Because right now, especially in Europe, we have the GDPR. Actually, it's more difficult, right? Actually, if you want to perform the user study, because it's more complicated to complete all the processes, right? All the steps there to get approved. Okay, and then we have the 2 traditional evaluation measures: false acceptance rate and false rejection rates. It's easy to understand. I won't explain this. Okay, and then we can see this is the results for the different classifiers. So we can see actually here we can see the third column. So average the error rate, right? Of the third row, yeah, the third row. So the average error rate. So we can see actually the RBFN actually can achieve the best results there, right? The lowest the error rates as compared to other classifiers. However, because it's almost 8%, right, the false rates, so it's still too high, right, in practice. So we need to further to decrease the error rate. So at the time we identified that, so normally a suitable classifier should provide a relatively small FAR, right? And the FAR, the error rates should be below the 5%, right, each. And the classifier should be economical, right, and also should be able to implement it on the resource constrained devices like the smartphones. And also the classifier should be able to handle the variations, the behavior variations, right, of the user's inputs. So at that time, we developed PSO RBFN, the classifier. So we combine these two, so we can further improve the performance. So I won't go into the details, but I can show the results. So later, after the algorithm improvement, so finally we can achieve the error rate around 3%. So we think at that time, right, it's it's good enough, right, to be considered, right, in both the literature and also the industry. Okay, and then let me introduce another work. So from Mario. So Mario at that time, he worked at Berkeley, right, with Dang Song. So actually, this work they submitted to CCS in 2012, but at the time it's not that easy, right, to publish the papers on the behavior authentication, and later they published this work in TIPS. So in 2013. So in this work, they also to investigate whether a classifier can authenticate users continuously, right, based on the way they interact with the touch screen. Okay, so first they investigate how users interact with the touch screen, right? So we can see this the users how to use the fingers to interact with the screen. So we can see actually the interaction, the location are different among different users, right? So it shows the feasibility, right? We can apply the touch behavior authentication on smartphones. Okay, and then they define two popular the user actions. So first is the sliding horizontally, right, over the screen. Right, for example, you can read some of the pages. And the second is the sliding vertically over the screen, right? You read the emails or some documents, right? So it's a bit different. And also you do a web browsing. Yeah. So actually there are two directions, right? Two directions, vertically or horizontally, right? Two directions. And then is that they also, right, they divided up the data records into individual strokes. A stroke is a sequence of the touch data that begins with the touching the screen and ends with the lifting the finger, right? It's similar to a touch behavior, touch behavior that. Okay, they use the machine learning algorithms. So the classifier should be trained at first and then, right, can enter the authentication phase. Okay, and actually they have more features, right, than the first work. They defined 30 features. So you can see the figure. It shows the information, right, among different features. So we can see actually the higher the mutual information rate, the better the feature. So we can see the stroke velocity actually is the speed. It's the speed, right? And also the finger, actually is the touch pressure, right? And also the direction of the touch stroke, right? These are the most actually these are the best features, right? They consider can be used to model the user's touch behavior. And also this work actually in line with the results in the first work because almost they rely on these main features here. Okay, and then they exploit the features in a 2D subplace, right? So they can see a class separation is feasible, right? To separate different users' stroke, right? And we can see the right plot shows the XY positions, so where the fingertip first touches the screen. So it's feasible, right, to apply their features to model the users. And these are some and later they have to decide how many strokes can be used, right, to train the classifier. They consider two classifiers at the time. One is the SVM and another one is the KN, right? So when deciding with a single stroke, they use the ER, the equal error rate. It's around 13%, right? So they find that when they have 11 to 12 strokes, the error rate can become smaller and become stable, right? Around 2 to 3%. And then they finally will be ended at 20 strokes. And further, they show some error rate, right? Ranges across all the usage scenarios, and also based on the some other scenarios in 2 directions, right? In 2 directions, and finally they can find that their method can achieve an error rate between 0 to 4%, right? And they also find that the error rates for users on the same phone are on average 2% higher than that for users the data collected on different phones. So this is an interesting observation. So maybe you can think about what's the reason for this, right? And the last, they have a remark there is that where the experimental findings, right, disqualify this method as a standalone authentication mechanism, right, for long time authentication, it could be implemented as the means to extend the screen unlock mechanism, right, as part of the multimodal biometric authentication system. Right. So actually, so this remark is feasible, is valid at that time, the 10 years ago. But right now, you can reconsider this remark, right? Because actually, you can think about how to make you can design a touch behavior authentication solely based on the touch behaviors, right? Okay, and last, let me introduce some of the challenges and some insights on this area. So we also have a survey paper in 2015, right? So at the time we summarize all the work, right, on the behavior authentication. So we can see the voice, the signature, gate, behavior profiling, and also the keystroke dynamics and the touch dynamics. So we can see, right, actually the performance and especially the error rates varied, right, among the different data sets and different user studies and different works. So it's very hard to compare, actually, it's very hard to compare all this work. But basically we can see the error is still a big challenge for us to implement the touch behavior authentication in practice, right? Because it's not realistic, because the usability is not that good enough, right? So that means we still have many chances, right, to focus on this topic and to explore how to design more robust the behavior authentication schemes. These are some potential improvements, right? So first is to apply the behavior biometrics to improve the security of the agile unlock patterns, because the agile unlock mechanism is one kind of the graphical passwords, right? And we can apply the behavior authentication to existing authentication mechanisms. So in that case, we can further to improve the security, but also we can rely on the existing usability, right? So we can make a balance. And then instead of users, we can authenticate the user's behavior when they perform some specific task or under some specific scenarios. So in that case, the user's touch behavior may become more stable. So at that time, we can have a more accurate the user model, right? Okay, and this we summarize some of the advantages and the limitations of the behavior of the touch behavior authentication. So for the touch dynamics, so the merit is that because we can provide continuous authentication, right? It's very good, because the traditional password authentication can only authenticate the users one time, right? And then it's usually we don't need additional hardware, right? Because for some like the fingerprint authentication, we still need to have a special hardware to scan the fingerprint, right? But for the behavior authentication, we don't need additional hardware. And for the challenges and limitations, the problem is that because the user's touch behavior is dynamic, and it's really hard to model the touch behavior when users freely use the phone, right? So yeah, it's a challenge. And the second the issue is that the authentication accuracy, the accuracy is not that good, right? So it's also a main challenge for us. So how to implement the behavior authentication in practice. And there's the challenges, right? So first is we have to think about how to select the features, right? Because right now, so I think after 2014, there are many studies published on the behavior authentication, right? Areas, but still, right? How to select a valid features is a problem and is a challenge, right? So how to model the user's habits, right? So we need to think about it, and how to make your scheme scalable, right, to different mobile platforms or devices, right? And then the algorithm development, right? There are many studies nowadays they focus on to apply and improved machine learning algorithms, right, to the behavior authentication. There are many works here, but yeah. It's still very hard, right, to say, right, because we don't have a unique platform. So for us to compare all these algorithms, right? So you have to think about it when you, for example, just to propose a new algorithm there. So you have to think about your contribution. And there's the user's behavior habits, as I just said, because it's very hard, right, to model the user's behavior features because it's very dynamic. And the user may change their behavior sometimes, right? So how to reduce the deviation, right? So one possible way is that we have to focus on some specific scenarios and when the users perform some specific task there, right? So their behavior may become more stable. And then is the user study, right? Because when we focus on such kind of the research on the human-computer interaction, actually, right? So we have to design a user study, and it's very challenging, right? Because we need enough participants, and then we need to analyze the results. So normally we prefer the participants have diverse background and from different places, but in practice, it's not easy, right? It's not easy. And there's the evaluation platform. As I just introduced, because we don't have a unique platform or the open source platform for us to perform, to compare different research studies, right, on this topic. So it's very hard, right? So it's very hard, and it's a good topic, right, for us to think about. So whether we can develop an evaluation platform there. So it makes sense, right? So in that case, so different researchers we can compare or proposed schemes, right? And then also there are some the attacks we can consider, right? The shoulder-serving attacks, right? Because the behavior authentication, of course, it can increase the cracking difficulty for attackers, right? But we still need to think about because some more advanced attacks, right? For example, the attackers can video record your input. Then maybe they can mimic your input behavior, right? Then how to handle the situation. And then it's the usability. Usability is very important. So because we know, so even for very secure application, if its usability is very low, then nobody will use it. Then it's useless, right? So that's why we need to make a balance between the usability and the security, right? And it's always a topic there, right? And there's the attacks, as I just mentioned. There's some new attacks appeared. So you can think about those attacks, especially some side channel attacks, right? And some attacks target on the sensors, right? Because the sensors are very important, help us record the touch events, right? Or the touch actions there. So if the attackers can compromise the sensors, so it can compromise the authentication mechanisms. Okay, then the future trend, of course. So nowadays we have the touch screen, the mobile devices everywhere, and also for the IoT environment, right? Because we can always touch those touch those devices, right? And to make an input. So it's a very popular direction, right? So can think about, right, how to address some challenges, right, in this direction. And also you can think about some healthcare wearable devices. It's also in relating to the behavior authentication. So we can propose some schemes there. Okay, so finally, I'd like to replay this video from IBM. Okay, so actually this is a basis, right? So we can think about how to design a more robust behavior authentication there. So normally we can consider some multimodal authentication, right? The schemes, or we can consider how to reduce the deviations, right? When the users input their behavior. So thank you very much. So this is the end of this talk. So yeah, I can check the questions in the chat. Okay, so thanks. If you have any questions, you can leave your questions. Thanks.
Thank you, Dr. Meng, for your valuable presentation. You see, at the beginning, I was having some problem in the internet problem. That is what I am unable to introduce you. Now, let me say, Dr. Meng is currently associate professor in the Department of Applied Mathematics and Computer Science, Technical University of Denmark. He obtained his PhD degree in computer science from the City University of Hong Kong. And his research interests includes cybersecurity, malware, and vulnerability analysis, task management, graphical password, intrusion detection, biometric authentication and security, smartphone security, and blockchain technology. So thank you, Dr. Meng. But actually, at the beginning, I was out of the network. That is what I am unable to introduce.
Thank you. Yeah,
from the audience, any?
Yeah, no problem there. Yes. Yeah, thanks to this.
From the audience, any question?
Yes, so I can see some questions. So maybe I can read and answer. So first question is why we cannot repatriate the fingerprints? right? So it's a simple question. So I think because for the behavior, for the fingerprint, actually it's the biometric authentication and it's a physiological feature, right? So we can use the fingerprint. So of course there are many attacks, right, on the fingerprint-based authentication. So you can check that. Actually, of course, we can do that. So no problem. So how to protect the fingerprint attack, right? So maybe you can combine it with the behavior authentication, so that the authentication mechanism should track both the fingerprint and the behavior, right? So it's more secure. So I'm not sure whether I answered this question. So maybe you can post some follow-up or some additional questions follow this. And then is the second question, isn't the password stored in form of an encrypted form using a symmetric encryption means? How is then malware threats? Isn't the password stored in form? Okay, because I know. So this question is regarding the password storage, right? How to store the password. So of course, as long as the password is stored right in the database, of course you can protect it. What I mean is that because when you input your password, right? For example, you use your mobile devices. When you input the devices, the malware actually can record, for example, can record the touch screen, and actually the attackers can know what you type there. So actually they can see your password. So they know they don't need to decrypt your password stored right in a database, right? So, and also we have some other side channel attacks. So actually the attackers can use some other ways to know what you input during your interaction with the mobile devices, or how to obtain your passwords, right? So of course, our malware should be a threat on the password, because they can stolen your password stored on your devices, or they can record the touch screen during the interaction. So when you input your password right there, so they can record. And the third question is how to minimize the error rates. Yes, I think it's a good question and always there, right? And this is the main reason why we don't have the commercialized behavior authentication right now. Right? So I think there are several ways. The first way is that we need to analyze or to understand the user's behavior, the user's habits, right? How they interact or how they play their mobile devices, right? So in that case, we can select some more effective or more valid the touch features to help us model the authors, to model the users. And second one is that we need to consider some special scenarios and to consider when the attackers or when the users they perform or they use some applications, right? Because in that case, some of our results show that right their behavior could become more stable, and it's easier for you to build an accurate user model, right, to help you to improve the authentication accuracy. And also, and of course, the last way is that you can, of course, you can combine the behavior authentication, right, with some other existing authentication mechanisms to develop a multimodal authentication mechanism, right? So of course, we can further to minimize the error rates. Okay, the next question is, how will this behave when a person is using gloves or wearing fingertip gloves? Yeah, I think it's a very good and interesting question. And I also think this question before, right? And it's the same also because, for example, when your finger becomes wet, right? So it's not that easy when you interact with your touch screen. So actually, I think on one hand, it relates to the hardware. It relates to the sensors, right? So in future, whether we have some more advanced sensor, right? So can help us to like, we don't need, we can perform the authentication using some touchless features, right? Because we have some, we don't need to really to touch the screen, but we can just close to the screen, and then it can know that, right? We may perform a touchless touch action there, right? So it could be an option there, right? Because it's very interesting. Because right now, if you like, if you use a glove or some other scenarios, if you cannot to maintain your touch behavior there, then you may increase the error rates there. So that's the reason why we don't have the commercialized product right now, because there are many scenarios that we cannot maintain the authentication accuracy. Yeah. Okay. The next question is there any application of graph theory in this method? As far as I know, I cannot say with 100%, but as far as I know, maybe not. Yeah, maybe not, because to apply the graph theory, it depends on where you apply the graph theory there, right? Because of course, we can apply some theory to the behavioral authentication, and there are already some there, but you have to check the state of the art, right? But as far as I know, not many, right? So it's still feasible, right, to apply the graph theory, but it depends on where you apply the theory. The next question is, how can we solve the problem regarding face recognition for people like twins? Okay, there's another very interesting questions. It's also similar, right, in the behavior authentication, because if two users they perform the touch very similarly, right, then how to distinguish the users there? It's always it's always an open challenge there, right? So of course, I think you still need to find some features that would be different among these two entities or among these two people, right? These two persons. So if you cannot find the difference there, then it's very hard for you to distinguish, right, the twins or the similar persons there, right? So even for the face recognition, so you can think about some other or to combine some other biometrics there, right? How they speak, right, or how they like to the retina or something, or some other behavior that maybe. So you need a multimodal authentication there, right? So if you only based on a single authentication method, I think it's very hard. Yes. The next question is, are you talking about the attack when you are talking about recording patterns? Yeah, there could be. And there are also some other, the malware, you can, I forgot the title of the papers, but you can check. Actually, they developed the malware. So as long as the users, they got infected, the application, the malware can detect whether the users input the password, and then they can make the touch screen, right? And then later, the attackers can see your password there. So it's easy. And then how about devices which do not have any method of input other than keystroke and mouse, which do not have any method of input other than. So because there are also some the keystroke and mouse dynamics, right? There are many research studies, right, on keystroke and the mouse dynamics. The keystroke and the mouse-based authentication. There are many work there, so you can check. because right now the touch screen, right, becomes more popular, right? So the research, right, moves to touch dynamics based authentication. Yeah, can you tell something about the relevant data set? Yes, I think it's a good question. So because you know, right now it's not that easy to publish the data sets because especially in Europe, because due to the GDPR, the process may be longer than before. And of course, we can, but very hard. So, but we can check some old data sets there, so you can use as a baseline to validate your schemes or proposed idea. So first one is, you still remember the second work I just introduced. So they actually published a data set there. So just search their paper title, and then you can find the data set there. So you can use that data set, right? And later I can see there are also some work. They also publish some data sets, so, but not very publicly used data sets nowadays. So we can always find some data sets published by some paper authors, right? So just check that. And it's also good for you to collect your own data sets, because it's your responsibility, right, to handle the data. Okay, the next question is, in Apple products, someone can easily change the screen ID and can change the face ID details easily. What can be done to prevent? I'm not quite sure about the question, because if they change the screen ID and the face ID, what's the impact of that, right? So to prevent, of course, you can have some, you can apply some mechanisms there, right? To, for example, if they want to change it, they have to authenticate, or they have to do some, they have to meet some requirements. So then they can change it, right? Otherwise, they cannot do it. Yeah. So maybe you can further explain it. Yes. Then how malware work? Yeah, I think the question is too general, right? Because you need to check the paper, because always there are some, because the malware, they have some permissions there, so they can connect and know the timing of when you input your password there. The next question is session identification. The purpose is to determine when a user session starts. What does it mean? Okay, what does it mean? Yes, because it means when you use the machine learning algorithms, right? Then you have to train the classifiers. Then you have to construct some signatures or patterns, right? You use the patterns to train the classifier. So one session means that how many touch action or touch events in this session, and then you can use the session to train the classifier, or how long the session could be. Then you may have many sessions, right? And you can use those sessions, labeled sessions, and to train the classifier. And then the classifier can to label the next session, right? The next session. So, and then we can decide whether it's a legitimate user or not. Yeah. And then I think this is the last question. I've heard about using light to extract existing patterns on touch devices due to the finger, smudging the touch device when drawing patterns. Can you discuss a bit more on it? Oh, okay, I think smudge attacks is very popular, and it's a very widely known attack right there. So actually we can use some the forensic techniques to recover our touch strokes on the touch screens. So it's easy to compromise the unlock patterns, right, on the Android phones. So So that means we have to further to improve the security. So we have to combine it with the behavior authentication, right? So as long as we combine the unlock mechanism with the behavior authentication, like the touch authentication, then the attackers need to know both the unlock pattern and also how you input the unlock pattern, right? Then it may increase the difficulty for the attackers, right? But if you only use the unlock pattern right there, then of course, as long as the attackers can recover your touch event, your touch trail there, then of course the attackers can know, can know how to unlock your unlock your phone. So the basis, do I still have time to answer the questions?
Any question? So anyway, thank you, Dr. Meng, for your valuable discussion and presentation.
Okay. Yeah.
So it is
Thank you very
nice
much.
that I think it will be helpful for participants a lot.
Thank you.
Okay.
Yes. Thank you
you
for
very
your
much.
attention.
See you again.
Yes.
See you again.
Okay. Thank you.
Okay.
Yeah.
Thank you.
See you.
The bus is Giri, sir. So, hello, student. Already we have. Sir, I think Giri, sir, there is some network issue.
Hello. Getting my voice?
Yes, sir. Yes, sir. Please, sir.
Hello. Are you getting my?
Yes, sir. Yes, sir. Yes, sir. Please, please.
Cryptography, information security, cyber security, AI security, privacy and trust. Now I request to Professor Sakurai to start your presentation. You are most welcome.
Just a moment. I try to upload my slide, but not work well. I don't know why. Host, give the permission to upload the file.
Yes, sir. It is there, sir. You have to just click on the share screen. At the bottom, there is mute, start video, participants, share screen. In the share screen, sir, you have to select the application that you want to present, sir.
The green button. Can you find the green button, share screen?
So first of all, you open the application, and after that you click on the share screen, and then you will find the application visible in the window, and then you have to click on share.
Hello?
Yes, sir.
Okay, I try again. That's okay. Oops.
Yes, it is coming, sir. Yes, sir. So please open the application that you want to show, sir. PPT, sir.
Oh, this one. Fine.
Yes, exactly. Yes, it is coming, sir. Please proceed, sir.
Yeah.
Okay.
Yes. Welcome.
Ready?
Yes, sir.
May I start?
Okay, fine,
Yes,
fine.
sir. Yes, please.
Yes, Sakurai, fine. Continue.
So thank you very much. Give the chance to this presentation, Professor Giri. The title is Attempt to Design the Post-Quantum Crypto System from the Ong Shinoa Shamiya via Sato Araki, Japanese researcher. Subtitle is Non-Commutative Structure Does Enhance Security. Okay. Origin of this talk is last time I did once the ICMC, the Professor Giri organized Varanasi, but a bit modified these 2 years progress. So Professor Giri asked me the more preliminary background before the main topics because it's true mathematics. But thanks to the excellent presentation, the survey by the Sadat Lake in this workshop, the last time, his title is a Challenge and Opportunities, Cybersecurity, Multivariate Polynomial and Lattice-Based Cryptography in the Quantum Era. Yeah. His talk is after Peter Shaw's inventing the post-quantum algorithm to break the RSA or discrete law. But this talk is something before the Peter Shaw. So including the research before 1990, including the Ong Shinoa Shamiya or Matsumoto Imai. Okay, so 4 major public key crypto system in this talk. The first one, the Ong Shinoa Shamiya, also Matsumoto Imai, and E sign, and N2. Most new one is N2. You know the Ong Shinoa Shamiya designed for improving the efficiency of the signature computation compared to the RSA. So they propose this kind of 2 variable signature scheme. Whereas Matsumoto Imai designs a public key encryption scheme with some extension field. Also, Tatsaki Okamoto, the same motivation with the Ong Shinoa Shamiya to improve the efficiency of the signature verification computation. So he proposed E sign. But the modulus is p to the 2 square q. So we discussed systematically in this signature schema encryption scheme from the point of view of the post-quantum cryptography. Already the previous talk, invited talk, keynote, explained the Matsumoto Imai scheme. But again, we recall the scheme consists of the 3 map based on the central map. This is a kind of the multivariate polynomial. Also, before, after we together concatenation of the affine to map. So nonlinear part is a central map. And we want to this map to be the one way. Invert is not so easy. Whereas evaluate the direction is easy because of just polynomial mapping. So secret key consists of these three mapping, whereas the public key is a concatenation. So security based on the getting the secret mapping from the public key is not so easy. This is the idea of the Matsumoto Imai. Also, we can both. We could implement encryption and signature by modifying this idea. Now the multivariate public key, we could say the one of the candidate of post-quantum crypto. But the origin of the Matsumoto Imai, it was 88. No yet the Peter Shaw's algorithm. So we don't discuss well the post-quantum computation. Rather, their motivation is using the empty hard problem, whereas the RSA or discrete may not be the NP hard. So thanks to the NP hard problem, the size of the secret could be smaller. Also, the hardware implementation is rather smaller compared to the RSA. That is the original motivation. So Matsumoto Imai, why they introduce a multivariate polynomial. But these days, thanks to the post-quantum crypto generation, the many variety of the modified scheme proposed based on this idea. So encryption scheme, including the simple matrix or ZHFE, also the signature scheme, including the unbalanced oil vinegar or rainbow. Later we discuss. Advantage is the efficient computations, encryption, decryption, and signing and verification. So what is a challenging issue in this area? The most important is security. So exact security, how much stronger complexity, the multivariate polynomial problem. And the other is some disadvantage of the longer key size. So how to reduce is one of our research result. And something a new application. So we'll summarize the history of the multivariate public key crypto system. Before Peter Shaw or after Peter Shaw. So 88, the inventor by the Matsumoto Imai, their paper is published in Crypto, Eurocrypt. Independent from the Peter Shaw's algorithm. 1998, Jack Patran did attack, broken the Matsumoto Imai scheme without quantum algorithms, direct traditional algorithms. And 1996, after the Patran's attack, some modifications, HFD, hidden field equation crypto system proposed, and balanced oil vinegar signature scheme proposed. However, the HFE was broken by Kipnis Shamir, 1999. Also, the oil vinegar did attacked. Furthermore, the modification 99 from balanced to the unbalanced oil vinegar signature scheme. So this also attack by employee. Some researcher from the Grosvenor base, the French researcher for jail, proposed the F4 algorithm. It's quite efficient for the Grosvenor base. It also works from the attack. Whereas the EU standard, the project was called NESSI. You may remember. Many crypto algorithms standardized by the NESSI. And one of the signature schemes, Splash, was selected as a EU standard. But as soon as this signature scheme also analyzed, and Jin Taisding proposed the rainbow signature scheme. It's a kind of the multi-layer unbalanced oil vinegar scheme. And the simple matrix scheme, the HFE, also still keeping the attack device modification a new algorithm until now. So this is a rough classification of the multivariate public key crystal system. The point is single field methodology or big field methodology or medium field methodology. So depend on the size or how to choose the base field. Some extended field extension. Rainbow and MOV using the single field method without extension, where the Matsumoto Imai scheme HFE using some huge side field after the extension. So one motivation is our research going back to the Ong Shinoa Shame scheme. Recall their scheme, the input, the given parameter H, message, and modulus N is the same as RSA, P product Q. We should find this solution XY. First, we expect without prime factorization P and Q, it's not so easy to resolve this equation. It's an expected security based on the hardness as RSA. That's why they propose very efficient. However, the designer, including Shinoa and Pollard, attacked 3 years later, resolve without factorization. They invent some direct algorithm to resolve this equation without P and Q. So one history for this area. So this chart shows how developed after Ong-Shneur-Shamir scheme from 1984. Two directions in this area. One is extending with multivariate. For example, birational permutation scheme. The other approach is changing the commutative computation to the non-commutative. So the Japanese researcher Sato Araki extends the Ong-Shneur-Shamir scheme to the quaternion. But story is both extension, the multivariate with a birational permutation attacked by Coppersmith. Also the quaternion scheme is broken by the Coppersmith. Still, Professor Tsuji, Japanese crypto researcher, investigating this approach, the multivariate. Also, the Hashimoto, younger Japanese researcher, extending these two approaches merge to the matrix. Furthermore, we extended this idea to more general post-quantum scheme. So this matrix scheme can be attacked by Uchiyama Ogura. At this moment, this matrix scheme is not yet the post-quantum, but we extending with Yasuda to the post-quantum. Now we see how we extend. So my motivation is how the extending this quaternion scheme to the more general scheme. So general means octanion. Because Sato Araki extending octanion to the Ong-Shneur-Shamir scheme. But sorry, this is broken. Maybe this is a quite fast approach from commutative to the non-commutative. So I invited the mathematics PhD student, postdoc student, to my laboratory 207. He is an expert of the number theory and the representative theory. Of course, octanion, you know, the non-commutative as a quaternion, but octanion is more restrictive, no more associated. So it's critical to apply the crypto system because the too restrictive, no associated. So he mentions it's almost impossible. So we may give up, but he extending from quaternion to extended the matrix because quaternion regarded as a special case of matrix. So general case can be regarded. So we presented his idea to 008. So first, the symbolic computation and crypto conference, Beijing. So Hashimoto's idea is using the non-commutative ring, but this still led to the modulus PQ. So note, indeed, this is a multivariate non-commutative polynomial matrix, but due to the factorization hardness assumption, this is not yet the post-quantum. He leaves 3 years working in the laboratory, so we invited a new mathematics postdoc researcher Dr. Yasuda. He also extending this Hashimoto idea for being the post-quantum. So I did quite simple, change the ring over the finite field. Extension is easy, but we should discuss the security of the design against the no attack. This is our main research. So recall the rainbow gene tiling proposed to 005. Not the exact scheme we describe, it's only idea or top high level description. Advantage is a very flexible selection of the secret key. And still secure. Still a candidate of the NIST post-quantum contest, third round, he survived. So it can be kind of the multi-layered, unbalanced oil vinegar signature. So look like the very beautiful the rainbow, but unbalanced size. So rainbow has some parameter of the V6. So Yasuda well classified from the point of the rainbow view. High level point to the previous scheme. For example, the Ong-Schnoyer scheme can be regarded as the special case of the rainbow K11. Birational permutation scheme can be regarded a kind of the special case of rainbow. Also, Sato Araki quaternion is a K rainbow 44. Also, Hashimoto scheme is not one but R. Anyways, in terms of the terminology of rainbow, we can describe the previous scheme well. It's a family of the rainbow. But the practical issue we have in the even rainbow, the long secret key size. It's one of the weakness of the post-quantum signature scheme, because 100 times longer compared to RSA. So the one challenge issue is how to reduce the key size. So we were more introduce the non-commutative to the non-commutative link from the commutative field replacement. So name is NC rainbow. This is an idea of the Dr. Yasuda. So to joint work with Yasuda and Takagi, the CTRSA, we presented some embedding of the public key into the rainbow from the non-commutative rainbow. So after extension of size, non-commutative rainbow can be embedded. This means it's kind of a compressed size. Some numerical computation. So non-commutative rainbow is some improving the performance of the key size, 20% around. So we believe advantage of the NC rainbow compared to the key size. The idea is kind of the simple structure of the extended field embedding. So we can skip this mathematical structure. It is a quaternion, come again. So large matrix can be constructed with a less parameter. It's a point of the idea. But sorry, after our proposal, the non-computer rainbow did attacked, broken by Tomae. He applied the mini rank attack and high rank attack. And also mentions the quaternion is more complexity for signing algorithm. So he mentioned not use the NC rainbow. It's one approach of the non-commutativity. So now we apply the lattice case from the commutative to the non-commutative, especially the N-true case we discuss. N-true also the design the Silverman mathematician, 1996. It's a lattice-based on the standard IEEE. And one candidate of the post-quantum still alive in the NIST competitive third round. Other lattice-based encryption, the small error probability. But they choose a specific ring, which for selecting, for reducing the error decoding. So we introduce the variants of the N-true. Origin of the N-true is this type of the ring and the mathematical formula, multiplication formula from this type. So our idea is to replace this ring to other variants. So two extension methodology is N-true to the more multi-variable. Other side is a non-commutative ring we introduce from commutative. So it's a kind of the metric case. The point is just link to the group ring. So a lot of the group ring we investigated because Dr. Yase is an expert of the representative theory. So he knows this kind of the space groups, cyclic, dihedral, Frobenius, GL, SL, and how we can express the N-true variant. The point is original N-true is a cyclic case of the group ring. So cyclic group ring, the original N-true. So this is a natural variant from the original N-true to with a general variant of the group ring N-true. See the size of lattice compared to the same size of the group. So you could see the lattice getting bigger. So original cyclic is the most smaller size. So we could extend it, but less efficient from the point of the size of the lattice. So this is my original summary or after the 5 years or 10 years research, I spend this area. So our approach is from commutative to the non-commutative, how much work where in the enhancing the security of the crypto. The point is, of course, everything is finite. So it's a kind of the matrix algebra. And the point of the complexity of the security. So we investigated the variants of the N-true, but the conclusion is original N-true cyclic case is most secure efficient. That means a simple cyclic case is the best. So extension is a kind of a trial. So going back to again my motivation. This is my motivation. After quaternion, is it possible to extend the octanion? Yeah, it's a negative because of the octanion don't satisfy the associative rule. So but here I may not give up my idea. So how to extend this idea? Octanion is a non-associate indeed, but we should analyze the difference, this gap. So some things are not exact, but could be working the approximation. Investigate this gap. It's small, something smaller. We could construct some pseudo algebra. So it's beyond the algebra, but some are using analysis with approximation. That is a kind of this challenging issue in this area. So okay. Ong-Shinoa Matsumoto Imai is a quite algebraic scheme, only algebra. But N-true E sign using the trick of the approximation. So still we may construct the beyond the non-associative world. So final conclusion. So the post-quantum crypto research still very active now. For example, before crypto, most post-quantum paper published in the PQ crypto was some smaller conference, but this is the first crypto paper accepted to 001, the Untitled. After that, many post-quantum crypto paper published, even this summer. Untitled also published some crypto analysis of the lifted balance or vinegar signature. Still a very active design analysis. Also, the September next month, middle, original the venue is Paris, but now the virtual, the PQC Crypto 2020. 2 session is a multivariate cryptography. So still attack paper or efficient generation of the rainbow. Keeping the research. The final remarks is area. This talk is background is post-quantum before Peter Shaw, but before Peter Shaw, before post-quantum, long-term security research has been discussed in this area. For example, original Matsumoto Imai motivation is a smaller hardware implementation with an anti-complete program. And time stamping, linking scheme, now applying the blockchain core technology, Harvard Stewart is invented in 1991. Also, the Johannes Buchmann, the long time discussed. How long we need the security in crypto? How long now? 20 years, 50 years, 100 years. Of course, quantum computer could be implemented successfully 20 years, before 50 years. But how is security we could guarantee the 100 years? How to evaluate so long? So it's a kind of the research in the beyond post-quantum. Some research paper published in the Bookman groups. Also, the not only security but privacy have been discussed. We should discuss as a future topics. So thank you very much.
So thank you very much for your valuable speech. So any question from the audience? Any question from the audience?
Yes, 7 questions. So first question, which is better, the symmetric key cryptography or asymmetric cryptography? Depends on the application. Of course, against the post-quantum computer, the symmetric key look secure, but of course, depends on application. We need both. But some researcher try to construct only symmetric key-based cryptography or everything. Of course, signature scheme can be implemented only symmetric primitive. Okay, so second question, the same research question. How the data signature works? So it could be the same questions. Some data signature can be implemented, even the hash function was symmetric based. So third question is the difference between the rainbow signature and the data. Yeah, rainbow is a kind of the data signature, special case. So fourth question is why does tuning commutative to non-commutative compress the size of the rainbow? It's a good question. We have a write paper. So can you please reference paper? But sorry, I mentioned we have non-commutative rainbow did broken. So we need more another approach. After taking the silver cybersecurity as a career with a future job scope. Yes, thank you. After 2 years, so most question fine. Yeah. So any more question? 7 question I did answer. So Professor Giri, you hear me? Professor Giri, you hear me?
Yes, sir, we can hear you, sir.
How is a research project in the Indian government or university or post-quantum research these days?
Giri, sir, are you able to hear us? Hello? Sir, there is some network problem in Giri, sir, side.
गिरी सर रीलॉगिन कर रहा है. There is some network issue, I suppose.
Okay, so may I close my talk? One more question come. Okay. Why does tuning the commutative to non-commutative compress the size of the rainbow? Same question. So check my paper, please, so that this is attacked. So very sensitive.
Devasis Giri, sir, hello.
Am I audible?
Yes, sir. Yes, sir.
Hello?
Please, sir.
Am I
Sir.
audible?
Yes, sir.
Okay.
Professor Sakuri, sir, has
Is there
completed his talk, sir.
Okay, okay. So, Professor Sakuri, thank you very much for your valuable speech and informative speech, and I think it will be helpful to our audience a lot. So, thank you very much, and I am sure that we will meet sometimes later in future.
Yeah, my
Right.
pleasure. Great honor,
Thank you
Professor
very much.
Giri. Yeah, I hope to visit you.
Yeah, we will. Yeah,
Yeah,
okay.
thank you. Thank you, the audience. Bye.
Devasis Giri, sir. Hello. Are you there? Devasis Giri, sir. Devasis Giri, sir, we are not able to hear you, sir. Please on your mic, sir.
So now our next speaker is hello.
There is some echo from your end, sir. Devasis Giri, sir. So, sir, we can proceed to next talk, sir. Devasis Giri, sir. Yes, sir. Yes, sir. We are able to hear you, sir. Yes, sir.
In the Department of Computer Science Engineering, IIT Madras, Chennai, under the supervision of Professor C. Pandurangan. Her research area interest includes design and cryptanalysis of public key crypto system and network security. She is currently exploring public key primitives such as proxy re-encryptions and re-signature, and exploring their proxy re-encryption technology. Arijit, you are most welcome to start your presentation.
Yeah, thank you, Debashish Giri, sir.
Okay,
Thank you for your introduction. So should I start the talk?
Yes, ma'am. Please proceed, ma'am.
Okay. So the title of my talk today would be Recent Trends in Proxy Re-encryption Technology. So this is basically a continuation of the talk which was given last week by Professor Pandurangan. So here will be the organization for today's talk. First, I'll be introducing and giving a quick recap to what is proxy re-encryption. I'll be talking about proxy re-encryption in the PKI framework. So I'll be giving its definition. I'll talk about its security models. Then I'll talk about the need of collusion resistance in the PKI framework of proxy re-encryption. I'll then give a brief description of our result obtained and then end the talk with some concluding remarks. So consider the following scenario. I have a user Alice who stores her files encrypted with her public key in the cloud. Now Alice wishes to share some of her files with another user Bob, but if you see over here, Alice's files are encrypted using her public key and they can be only decrypted using her secret key. So what is the naive solution in which Alice can share her files with Bob? The naive way is that Alice has to share her secret keys with Bob so that Bob can decrypt the file, right? But if we do so, Alice is going to compromise her privacy. So an efficient solution to enable such kind of encrypted file sharing is called as proxy re-encryption. So in this scenario, what Alice is going to do is, Alice is going to generate a special key, which is called as a re-encryption key, and will send it to the cloud server. Now the cloud server will act as a proxy. So we call the cloud server now as a proxy server. Upon receiving this re-encryption key, what the proxy will do is, the proxy is going to re-encrypt the file. So the files which were previously encrypted under the cipher, under the public key of Alice, with the combination of the re-encryption key, will now be decryptable by the secret key of Bob. And what is important to note here is that the proxy, which over here is the cloud server, should not learn any information about the underlying file. So since Alice delegates her decryption rights to Bob, Alice is called as a delegator and Bob is called as the delegatee. And upon re-encryption, the cloud is going to forward the file to Bob. Now, proxy re-encryption is in huge demand in the industry because of the properties which are exhibited by proxy re-encryption. So some of the most desirable properties are unidirectionality and bidirectionality. So in the unidirectional framework, what happens is, given a re-encryption key, the proxy can re-encrypt files from one user to the other, but not the other way around. So over here, the re-encryption key will enable the proxy to re-encrypt Alice's files towards Bob, but not Bob's file to Alice. In the bidirectionality setting, the re-encryption key will enable re-encryption in both sides, that is, both Alice's files to Bob and vice versa. Another yet important property of proxy re-encryption is the single hop and multi-hop setting. So in the single hop setting, the re-encryption key will enable the encryption of Alice's files towards Bob only once. In multi-hop setting, the file can be re-encrypted polynomial number of times. So I'll be next talking about the definition of a unidirectional proxy re-encryption scheme in the PKI setting. So if you remember, Pandurangan sir had discussed about the identity-based setting. So in this case, we have the following algorithms. First, we have the setup algorithm, which will take as input a security parameter kappa, and it is going to generate the public parameters params, which will be used by all the users in the system. Next, we have a key generation algorithm, which will be run by every user in the system to generate their pair of public key and private key. Next, we have a re-key generation algorithm, which will be run by the delegator. So in our case, the delegator was Alice, if you remember in the previous diagram, who wants to delegate her decryption rights to Bob. So in this algorithm, Alice will take as input her secret key, her public key, and the public key of Bob, which is PKJ, and the output will be the re-encryption key that enables re-encryption of her files towards Bob. Next, we have the encryption algorithm and the decryption algorithm. So the encryption algorithm will be run by any user who wants to encrypt a particular file, say M, towards Alice with a public key PKI. And the algorithm will generate an original ciphertext, which is called as CI. And the decryption algorithm will enable decryption of the ciphertext CI only with the secret key of Alice, which is SKI, and output the message M. Next, we have the re-encryption and re-decryption algorithm. So what the re-encryption algorithm does is, this will be run by the proxy. So the proxy will take as input the original ciphertext CI, which was initially only decryptable by Alice's secret key, the re-encryption key that enables encryption from Alice to Bob, and the public parameters, and it will output a transform ciphertext, which is GJ. Now we have the re-decryption algorithm, which will take as input this transform ciphertext, which is DI, and it can only be decrypted using the secret key of Bob, and the resultant will be the plain text M. So we have to talk about the correctness of the proxy encryption scheme. So what does it say? So for the original ciphertext, that is CI, which was generated, all well-formed ciphertexts, which is the encryption of the message M from the message space M, the well-formed ciphertext should always be decryptable to output the original message M. And the consistency of re-encryption and re-decryption algorithm says that all well-formed transform ciphertext should be decryptable to output the original message M. So next, I'll talk about the security notions of proxy encryption. So the security notion of proxy encryption is usually defined by provable security. And because we have two levels of ciphertext, which was the original ciphertext and if you saw the transform ciphertext, so we will talk about the security of both levels of ciphertext. All right. So first I'll talk about the security notion of original ciphertext. And this is the highest level of security, which is called as chosen ciphertext attack. All right. So this security is shown in the form of a game between two entities, which is a challenger and the adversary. So it is a reductionist proof in which these two entities, challenger and adversary, are going to interact with each other, where the goal of the challenger is to break an underlying hard problem, and the role of the adversary is to actually break the particular scheme. So what we say is, if the adversary is successful in breaking the underlying scheme, then using his solution, the challenger can actually break a hard problem. Okay. So this game takes place in the following 4 phases. So first, the challenger is going to run the setup algorithm and generate the system-wide public parameters. The adversary, upon receiving the parameters, is going to enter the first training phase, that is phase 1, in which he's going to train and learn various inputs from the challenger. So he can generate various queries, for example, key generation queries, decryption of some ciphertext, re-encryption queries, and the challenger has to respond accordingly. After this training phase is over, next the adversary will enter into a challenge phase. So what it does is, it will send a public key of its choice, PK star, and 2 messages M0, M1. It is to be noted that the adversary should not have queried the challenger with this particular input in the first phase, that is phase 1. What the challenger does is, given these 2 inputs, M0 and M1, it will pick an arbitrary message of its choice, encrypt it under this public key PK star, and generate a challenge ciphertext C star and send it to the adversary. Now, what the goal of the adversary is that, given this challenge ciphertext C star, it should be able to identify which was this particular message, whether it was M0 or M1, that was picked by the challenger to encrypt this particular message. All right. Upon receiving the challenge ciphertext, the adversary will enter again the second phase of training, similar to the first phase, but it cannot generate any re-decryption or decryption queries for the challenge ciphertext. So it is a trivial constraint on the adversary. Finally, the adversary is going to output its guess of B, that is whether it is 0 or 1. So if the adversary has correctly identified this guess of B dash, that means it has won the game. All right. So this is the first level security, that is the security for the original ciphertext. And we also have the second level of security, which is called as the transform ciphertext security game against the chosen ciphertext attack. So the only difference between this and the previous game is that in the challenge phase over here, the adversary is going to be challenged with a re-encrypted ciphertext, that is a transform ciphertext. All right. And the game is secure if the advantage of the adversary is negligible. That is, it can obviously guess what the particular bit was with a probability half, but it should not have an advantage more than that. So next I'll talk about collusion attack. So all the previous schemes in the literature are vulnerable to this particular attack called as collusion attack. So what exactly is this? So what happens is, usually the proxy has the knowledge of the re-encryption key. The proxy and a malicious delegatee Bob can actually collude, and they can recover the secret key of the delegated Alice. How is it possible? It is because the re-encryption key which is generated is actually a function of the public key of Alice, the secret key of Alice, the public key of Bob, and the public parameters. So it is a natural question to ask whether the secret key of Alice can actually be generated. And what we saw is all the previous schemes are actually vulnerable to this kind of attack. And it's actually important because if the cloud as well as the delegatee gets access to the secret key, then the security is lost. The identity of the delegator can actually be stolen. So here is the scheme. So this was the first proxy re-encryption scheme, a very famous proxy re-encryption scheme by Blaise, Blumen, and Strauss. So this was how the re-encryption key was generated. And we actually see there is a collusion attack in this scheme. So how is this scheme generated? So over here in the public parameters, we have a group G, and we have the small g is the generator of this group. And the group has to be a prime order group, and the order is P. So we have the delegator and delegatee, Alice and Bob. The private key of Alice is an integer A, and the public key will be the generator raised to the power of A. Similarly for Bob, his secret key is B and the public key is G raised to B. How the re-encryption key is generated is A over B, where A is the secret key of Alice and B is that of Bob. So suppose over here, I have the re-encryption key. The re-encryption key is with the proxy, which is A by B. And now he colludes with Bob. So Bob's secret key is B. So what they'll basically do is they'll multiply this re-encryption key with the secret key of Bob, and they can actually recover what was the original secret key of Alice. So this is a very trivial attack. And what we saw is the first scheme was vulnerable. So similar to this, many schemes which were initially devised are vulnerable to this kind of attack. So next I'll talk about another preliminary, which is called as bilinear mapping. So bilinear mapping is a kind of function which is used in cryptography, a very common function. So this is used because it has a lot of advantages, which I'll discuss later. So bilinear pairing basically is a function which maps two elements of one source group, which is G, to a target group GT. And what is interesting over here is that suppose it takes two elements, G raised to the power of A and G raised to the power B from a source group G, in the resultant output, usually the exponents are multiplied. So this is a very interesting property which is used in cryptography because it helps in the ciphertext validity. And it is a very useful technique which is used in this unidirectional transformation in proxy encryption schemes. And what we have seen is most of the existing schemes use this particular technique to generate proxy encryption. So here are the results in the literature of collusion-resistant unidirectional proxy encryption schemes in the public key setting. And what we have seen is all of these schemes make use of the expensive pairing operation. And why I call it expensive, because one pairing operation takes more than 5 times the time taken by a simple modular exponentiation operation. So although it makes the scheme easy to devise, but it takes a lot of time and it may not be suitable for many applications. So what we have done is we have devised a scheme which is CCA secure unidirectional, and we show that our scheme is pairing free. That is, we do not rely on pairings. We have just used modular exponentiation to obtain a CCA secure scheme. And our design is based on Elgamal encryption. So it is a very standard classical encryption scheme and Schnorr signatures. And this paper was published in CANS 2017. And it's a joint work with Dr. Sharmila and Professor Pandurangan. So next I'll be giving a description of our scheme. So as I've already told, this proxy encryption scheme will consist of several algorithms. So next I'll be talking about the setting of all these algorithms. So first we have the setup phase. So over here, a group G is chosen, which is of a prime order, say Q. And my small g is the generator of the group. And we have several hash functions, which I have not written here due to space. I'll be explaining them as and when in the course of the presentation. Next, we have the key generation algorithm. So for every user I, the secret key is first selected by choosing two random integers xi1 and xi2. And the public key is generated by raising these two secret keys to the generator G. So I have two components of the secret key and two components of the public key for every user. So here is how the encryption and decryption works. So this is the normal or the general encryption functionality which the scheme exhibits. So for encrypting a message M towards a user I, what a sender will do is he's going to pick an integer U and a string omega. All right. Next, he's going to compute a value R as the hash of the message and the string omega. He's going to compute several ciphertext components, that is D, E, as follows. So he will compute D as the public keys raised to the power of U, the U which is the random integer selected, and E will again be this public key raised to the power of R. Okay, so this is the first blinding we are doing. For the second blinding, we are going to compute D bar, which is basically hash of all these components, the public keys and the components DE which we have generated raised to the power of U. And similarly, we'll compute E bar as the hash of the same components raised to the power of R. Finally, we'll compute F. So this is the Elgamal encryption scheme. This is how the scheme is followed over here as the hash of G raised to the power R, which will be blinded with the message. And next we have the component S. So this is the signature over here. And the output over here, we'll be outputting only the components E, E bar, F, and S. All right. For the decryption algorithm to work, it will take as input the ciphertext CI and the secret key SKI. So SKI is the user and only he is entitled to decrypt this particular message. So given E, E bar, one can easily compute D and D bar using normal arithmetic. And then they'll have to check the validity of the ciphertext. And they'll have to recover the message, the original message M. So this is again very straightforward to follow. So given F, they will just do a XOR of the hash of this computation. So what you can see in the exponent is the secret key. And they'll generate the original message M. And if invalid, it will generate a bot. So this is how the re-encryption key is generated. So suppose user I wants to re-encrypt his files to user J. So what user I will do is, he's going to first pick a string H and another string pi, and he's going to compute the following components. He's going to compute V as the hash of these two strings, which we just chose at random. The component V as the public key of the delegated raised to the power of V. Then we have the component W as the XOR of this hash value of G raised to the power of V with the two strings which we just chose. And K is basically this value H over the secret key of the delegator. And he's going to send the values K, V, and W to the proxy. Now what this proxy will do upon receiving this re-encryption key and the original ciphertext is, he's going to compute D and D bar. And he just will do one computation. That is, he will raise the original ciphertext component E to the power K. So over here, if you see, E is the ciphertext component of CI and K is the re-encryption key component. All right. And the other components are as it is. So the new ciphertext is E bar, F, W, and F, V, and W. So this component will now be sent to Bob. Okay. So over here, my Bob is a delegatee. And what Bob will do over here is, he will take as input his secret key, and he's just going to recover these two strings H and pi by simply XORing the component W with his secret key, and then recover the original message M. All right. So how do we show that this scheme is collusion resistant? So over here, the game of collusion resistance is similar to that of CCS security. That is, it is shown in the form of a game between these two entities, challenger and adversary, where the goal of the challenger is actually to break an underlying hard problem, and the goal of the adversary is to break the scheme. So over here, the various phases of the game are, in the challenge phase, first the challenger, in the first phase, the challenger is going to run the setup algorithm and generate the public parameters. The adversary can next ask various queries to the challenger to train himself. That is the key generation queries, re-key generation queries, and the challenger has to output accordingly. Finally, the adversary is going to generate a secret key and a public key pair, all right? And this should be a pair of an honest user. What do I mean by an honest user? It means that the adversary should not have queried the secret key corresponding to this public key before in the training phase from the challenger. And if the adversary is correct, so the adversary wins the game, all right? And the scheme is secure if the advantage of this adversary is negligible. So we show that our scheme is collusion resistance under the following assumption. This is the hardness assumption which we use, that is the discrete logarithmic assumption in a group G. So given a generator G and G raised to the power A, it is hard to find out this integer A, all right? So this is my discrete logarithmic assumption. So how does this proof work? So here is the reductionist proof for our algorithm. So the challenger will be given the instance of the hard problem. That is, the challenger is given G and G raised to the power of A, all right? And what is the challenge? The challenge is he has to find out what is this integer A, all right? So next I'll show the derivation of how A is computed. So as I've already said, we have the key generation queries which the adversary can ask the challenger. Okay, so whenever there is a key generation query, what the challenger will do is it is going to pick two integers xi1 and xi2. All right, and given these two integers, it is going to set the public key pki1 and pki2 as follows. It will raise the pki1 as g raised to the g power a. So over here, if you see, it has injected the hard problem g power a over 1 over the remaining components are all known to the challenger. And similarly for pki2, it will raise g power xi2, which is again known to him, over g power a. So it only has to send the public key to the adversary. So over here, the components pki1 and pki2 can be computed by the challenger, right? The only challenge is it does not know what is the underlying secret key, but it does not have to actually display what is the secret key corresponding to this public key, right? It only has to generate this public key and public key components. So implicitly, if you see, the secret key has these elements A in it, all right? So particularly, if you see, the second component of the secret key is actually minus A plus xi2, where xi2 is a component which is known by the challenger. Finally, now in the output phase, if that adversary has correctly output the secret key corresponding to this public key, that is ski star 1 and ski star 2, the challenger can now easily compute A. How? By simply subtracting the value of ski2 with xi2. All right. Why? Because if you see how it was computed in the secret key during the uncorrupted key generation algorithm, it was only minus A plus xi2, right? So from this term, if I just subtract this value of xi2, I can actually obtain the value of A. So yeah, this is how the reduction is. So first, the challenger is given as input the hard problem instance G and G power A. Now the challenger is going to devise these two components of the public key, pki1 and pki2, in an intelligent way, so that it injects the hard problem into it and sends it to the adversary. The adversary now does this computation, whose job is to break the scheme. All right. So it has been successful, suppose, in breaking the scheme. And so it has output a valid secret key pair, that is secret ski1 and ski2. All right. And if it is a valid secret key, the challenger will use this output to generate the solution for the hard problem. All right. So over here, it is actually found the solution of the discrete logarithmic problem. So since breaking the discrete log problem is hard, so it is assumed that the adversary cannot break this scheme. That is, it is collusion resistant. In a similar fashion, we can show that the security of the scheme against a CCA adversary is actually secure based on the computational Diffie-Hellman assumption. So what is this computational Diffie-Hellman assumption? It is that for a group G, given the generators G, G power integers A and G power B, it is hard to compute G raised to the power of AB. All right. And similarly, we show this security of the re-encrypted ciphertext based on the computational Diffie-Hellman assumption as well. All right. Given all the, as I've already said, all the existing schemes are based on bilinear pairing, right? And out of all those schemes, only one scheme, that is by Libert and Benoit of 2008, was the most efficient scheme out of all the existing schemes. We show that our scheme is much faster than their scheme. So if you see, these are the various time complexities of the various algorithms, that is key generation, re-key generation. And by TE, I mean the time taken by a modular exponentiation. So one modular exponentiation is generated by TE, and TBP is the time taken by bilinear pairing operation. So you can compare it as one TBP is almost equal to 5 times TE. All right. So if you do the math over here, we have actually shown that our scheme is much faster than the existing scheme because it does not rely on pairing. So this was the application which was discussed with Professor Pandurangan in the previous lecture as well. So the various applications of proxy encryption are as follows. So nowadays it is very much useful in blockchain powered distributed storage. So it enables secure sharing of files in blockchain enable distributed storage. And apart from that, yeah, it has been successfully implemented by various companies. For example, NewCipher is a company which are actually using proxy re-encryption to enable distributed file sharings. Next, another compelling application of proxy re-encryption is encrypted email forwarding, where suppose you have a user Alice who is on a vacation and wants to delegate her decryption rights to her assistant, say Bob. So it only has to apply this technology of proxy re-encryption to enable such kind of email forwarding. Similarly, there are other applications. For example, you have outsourced filtering of encrypted spam, and you have Apple iTunes DRM. So the main, as Sir had discussed in the previous lecture, the original motivation of proxy encryption actually came from this Apple iTunes DRM. All right, so as I've already discussed, our scheme is pairing free and more efficient than the existing scheme. And it is the most efficient scheme in the literature. And it is secure under the CCA model under the CDH assumption. So as an extension of this work, it would be very interesting if someone could design a collusion resistant PRE scheme in the multi-hop setting. And also this work was based on the random oracle model. All right, so if someone can actually come up with a scheme in the standard model, it will actually be even more interesting to see the work. All right, so that's all from my side.
Thank you, ma'am. Devasis Giri sir, are you there? Devasis Giri sir?
Getting my voice? Hello? Hello?
Yes, sir, we can hear you, sir.
Hello?
Yes, sir.
So, is there any question from the audience?
I think I can see one question. So, ma'am, is this the same way that Google Drive works? When we upload a file for someone, we get a shareable link and we send this link to that person who will either view or download the file. No, so this is not the same way, because when you are uploading the file, it is not in the encrypted form. So over here, the Google Drive works in a different way. It is by the standard security policies are actually implemented. So Google Drive does not work in the same way. Any other questions? Digital signature, I'm not sure if that is relevant to this talk. Any other question?
For the participants, if you have any questions, you can post the questions in the chat box or in the question answer section. Giri sir, hello, Devasis Giri sir.
So
Yes,
audience, any question from your end?
Yeah, ma'am, is it safe? Someone has asked. Yes, I've already told it is CCA secure, right? So because it's CCA secure, it is safe. So that is the standard security notion which we follow. Ma'am, why does pairing take more time? Yeah, so pairing, the underlying operation in pairing, it's a function. So that is how the function is devised, all right? So it will map two elements of one group to another group. So yeah, so the implementation takes more time compared to normal arithmetic, modular exponentiation arithmetic. So the next question is, I mean, anyone who has the link can steal the data. Yeah, that's how it works, right? In Google Drive. So it asks you for the shareable link. So only people with that particular link can actually access the data. I'm not sure if steal is the right word, but anyone who has the link will have the data. So it depends on the user, what permissions you are giving, whether you give the editing permissions or the viewing permissions. Only those people. So these are the policies, the sharing policies of privacy. So proxy encryption is not used in such a scenario. Any other questions? Ma'am, what is the notion of training in CCA model? I didn't get your question. What do you mean by notion of training? I gave you the framework, right? How it works, like for the CCA setting, that is the chosen ciphertext attack setting. So you have the challenger and adversary who are going to play a game between them in the 4 phases. So we have the first setup, and then you have the training phase, phase 1, challenge, and then the training phase 2, and then the guess phase. So finally, if the adversary is able to break the scheme by correctly guessing what was the original bit of the message encrypted, it wins the game. So that is how the training. So by training, it actually means what are the questions it can ask, all right? So it will ask various questions to the challenger, and the challenger will give you the output. So it is basically what kind of data. So whether will I be able to get any information from any other data which I can collect. So CCA secure scheme says that even if you get any kind of knowledge from the other data, still for the particular data, you will not be able to decrypt it. That is what the notion of CCA security states. All right. Any other questions?
Any question from the audience? So if there is no question, then thank you, Arinjita, for your valuable speech.
Thank you, sir, for the opportunity.
Okay. We will be in touch if some information is required from our audience. Then I will
Sure,
talk to you.
Sure.
Thank you very much for your
Thank you,
presentation.
sir.
Okay. Thank you. See you later.
Sure, sir.
Okay.